Thanks a lot for, thanks a lot for the introduction. So what I would like to do in the two lectures that I have, one today and one tomorrow morning, is to see how we can use electron to actually look at optical property of materials. This is really an introduction, so I'm not going to go to very, very complicated stuff. It's more a way for you to see if you're looking at material that maybe have optical property, to say, hey, maybe that could be a nice way of actually looking at my material. So today we're going to actually look at how electron can look at those optical property, and we're going to look more at the static part. And tomorrow we will look at how we can use time to look at the dynamic. Okay, so we are talking about nano-optics. And what is exactly nano-optics? The idea is that nowadays we have those kind of material where we can have very, very small cubes of gold or just a few atomic layer inside a semiconductor, or even 2D materials. And all of them have very, very interesting optical property. But it means that the shape and the size of those different materials completely connect and explain the optical property that we see. So we need something that enables us to study this optical property, but at a nanometer scale. And that's where electrons are coming into play. So when we are talking about optical property, what exactly do we mean? Well, if we have a nano object here and we excite it, well, there is different things happening. There is absorption of the excitation, there is scattering from the nano object, and there is emission. So if we're actually looking at EELS, I will go a little more into detail, but it's basically looking at the electron after interaction with this nano object. What we are looking at is scattering and absorption, what people call in optics extinction spectroscopy. But we can also look at the light emitted by this nano object. And in this case, what we are doing is called cathodoluminescence, where basically we use usually a parabolic mirror to collect the light coming out of the sample after electron excitation and look at this light. So we have two different techniques using electron to look at optical property. Cathodoluminescence, that is usually going to be called CL in my talk, and electron energy loss spectroscopy. But nano object is really broad, right? So I decided to divide it in two different parts. Basically, metallic nanoparticles and semiconductors. And we will see for each of those two how electrons can be useful to look at their optical property. Okay, so we will start with metallic nanoparticle. And to start, I will ask a question. It will be a way also to check if it's going to work for the rest of the talk. So you can actually scan the QR code that is on your screen. You can also do it if you're online. And try to answer the question, what happens when an electron travels close to a metal? And usually I should be able to start. So you should be able to answer. And because you already had so many talks that actually mentioned plasmons, I'm pretty sure you can answer. Is it working?
Yes, yeah.
Okay, cool. Perfect. Okay, I will stop. So actually all the answers were correct, especially it's too late for this kind of question. And we will see in this talk how we can see all those different things about the material looking at electrons and how they travel close to the material. Okay, so exactly what happened when we have an electron close to a metallic particle. Your electron is actually a very, very, very small charge object that is going super, super fast. So close to a particle, usually when you're around 200 kilovolt, the time of travel is a few femtoseconds, which means that actually, whoa, that went way too fast. Okay, spoiler, okay. So which means that your electrons can actually be considered a pulse of electromagnetic field, very, very short, and therefore very, very broadband. So it's like having a white light going really close to your sample with a large evanescent field. And therefore, when you arrive close to your metallic particle, it's going to polarize your sample. And because you polarize your sample, it actually launches an evanescent field that your electron can feel back and lose energy. So actually what you're probing when you're looking at your electron after interaction with your sample is a loss of energy to this magnetic field that it actually created on the sample. So something that you have to remember is basically you have a fast electron that is like a white light source in our case. You generate an electromagnetic field inside your particle, your metallic particle, that's going to act back on it and lose energy. And what you're looking at is the loss of energy from your initial beam to the end, which is your electron energy loss spectroscopy. Okay, if you're looking at a bulk materials, what's going to happen is that you're going to polarize the electron of your valence band of your metallic particle, and you're going to basically launch a longitudinal wave because you're going to compress the electron in this direction. It's going to oscillate like this. So it's actually similar to a sound wave. And because it's similar to a sound wave and it's longitudinal, then you have no coupling to the light field. So it's not creating any light. However, what's nice is that because it's connected so much to the electron of your material, this is actually very, very connected to the property of your material. It's really a fingerprint of the electron density. So if you look at the plasmon bulk, then you will see that it depends quite a lot of your material, which energy is your bulk plasmon. And the width here is actually connected to the damping, so how it's going to relax into the material. But now, if we look at a nanoparticle, and therefore to something with a surface, what's going to happen is that you're going to create a surface wave here. And because you have a surface wave at the surface of your material, you have a part of the electric field that go out. And because it go out, you have actually an evanescent field within the vacuum, which means that this is able to couple to the light field. So basically, you have different conditions for this light wave to exist. It needs to propagate. So that means that the real function needs to be different from 0. And because we want something that coupled to the light and that therefore has an evanescent field in the z direction, in the propagation of the electrons, then you need an imaginary part in the z direction that is different to 0 also. And that's completely conditioned your dispersion curve. Which means that if I look at the dispersion relation of this kind of surface plasmon here, you see that there is a part that is really, really close to the light. So when you have those kind of very long surface like this, where you have actually something that is way longer than the wavelengths that you're looking at, you have something that travels, and you have something that is very much connected to your light. So you have a behavior of a light wave within your material. And that's what we call a surface plasmon polariton. If now you reduce the dimension, so instead of having in this direction something that is way longer than the wavelengths of light, you actually start to have confined state. And in this state, this is coming to become electrostatic and really just a density wave here, charge density wave going back and forth. It's going to be very close to a quasi-static kind of behavior. And because of this, this is completely connected to the geometry of your material. So actually what you see here is a decomposition of the different wavelengths depending on the eigenmode of your structure, just taking into account the geometry. And you see different wave, different geometry, giving you different charge density. And that's going to mean that you have your dispersion curve before, but now you have very specific position for your wave, for your quantification here. That completely depends on the geometry of your material. But of course, at some point, you need to add the material part of your structure, and therefore that's going to also determine the energy of the different plasmons. So that's actually a simulation done by Ugo Lorenzo Martin. You're going to see his name a lot during his talk. I really advise you the first chapter of his thesis that is also published in this journal. where he explained all of this very beautifully. And you see that depending of the metal you're looking at, actually the mode are shifted. But it's always the same mode, that they will always have the same shape, just the energy is shifted because the material is a little different. That's actually nice. We have 3 different materials: bulk plasmon, surface plasmon, polariton, localized surface plasmon, that completely depend on the shape. So we can actually try to classify them a little. If you go to very, very small thing here, your nanoparticle is going to be really, really close to a molecule-like kind of behavior. So actually, this is where you have all the quantum effect, excitonic resonance, and you can explain everything with quantum physics. If you go to this kind of, let's say, scale between 1 nanometer and 100 nanometer, this is where you have the localized surface plasmon, the quasi-static wave, and that what we just saw. And if we go to longer material, then here you're starting to have longitudinal surface plasmon, polariton, that basically travel, and therefore you have to take into account retardation effect. The interesting stuff for theorists are actually in those 2 gray areas here, where it's actually quite difficult to know when you need to start taking into account the retardation effect, for example, and go from a very quasi-static kind of decomposition to something that really is able to travel. And here, where you go from something that you can completely explain with classical electromagnetic field to something that is completely quantic. And what's happening here, which is basically cluster physics, so when you have a lot of really small particles together, and here it's close to what we call whispering gallery mode, where you have big, for example, big sphere here, where your plasmon travel around the sphere. So that's much more difficult to explain theoretically. If we stay in this area, which is between 1 and 100 nanometer, this is an area we like a lot for electron microscopy. This is the kind of scale that we are comfortable with. Then actually, well, this is true for every time, but what I'm going to show and the formalism that I'm going to show, which is going to be light, I promise, it's especially true for where you have a length of your nanoparticle that is smaller than the wavelengths of light. So if you're in this kind of scenario, then your plasmon here, your plasmon is actually what you're probing with your electron beam is actually the electromagnetic local density of state. Basically, what it means is how easy it is to populate your particle with plasmon at a specific position, when you excite at a specific position. And please stay with me, but we are going to try to explain this formula. So this is the formula that I choose. There is a lot of different formalism. This is from the paper of Arthur Loskin and Mathieu Kosiak, that basically developed the probability of exciting your material. So this is the EELS probability. So probability of exciting the material at a specific position. This is the R here, depending of your material and the property of your material for surface plasmon. So there is a few things that I want to point out. The first thing, okay, this is a probability of interaction between your particle and your electron beam. This is depending of the position, okay? So this is why we are talking about mapping. Depending of the position, that's going to change, depending of the position of the electron beam, and that's why we are happy to have a very small probe. As you can see, it depends actually of the imaginary part, and that's because of the thing I said to the beginning, that the EELS was actually sensitive to extinction probability and not emission probability. You have what we call the mode susceptibility, which is basically how easy it is to populate this mode with your electron. And as you can see, it of course depends on the frequency, so which wavelengths are you looking at? And this is really, really important. I'm only sensitive to the electric field along the electron trajectory. So we're actually looking at the electromagnetic local density of state in the Z direction, so the Z component here. But what you have to really take in mind is that keep in mind that if you do electron energy loss spectroscopy for those kind of metallic particles, what you're going to look at is actually mapping the local density of state in the Z direction, the Z component of the local density of state. That's actually super nice because it means that with a nanometer resolution, you can actually access the different plasmon mode of your nanoparticle. You can see here the dipolar mode, here the second and the bulk mode, whispering mode, I think that's the last one. So that's the first experimental paper looking at plasmon and mapping the MLDOS at the nanoscale using electrons. Since then, this is 2007, there was a lot of activity. I put a few here, but of course, this is a booming field. A lot of people are using it just to characterize now their nanoparticle. This is done in a daily basis in a lot of electron microscope. Okay, so we talked about basically absorption. And what we saw is that actually our excitation was more like a white light than just a single wavelength. So let's correct this drawing as we go. But we launched our plasmonic structure, our plasmonic mode within our nanoparticle. The question is what happened next? Of course, what happened is that at some point it lost coherence. You are launching an electron wave, an electromagnetic wave within your nanoparticle. So at some point it lost some coherence. And so how does it lose coherence? Well, it's only a few electrons that go out and suddenly it's a mess. And what happened is that it arrives in a very small time scale, between 1 and 100 femtosecond. This is what we call a really poor oscillator, right? It doesn't keep the excitation very long. And what can happen for you, this loss of coherence, is either emission of light, interurban transition, what we call Landau damping or phonon damping. When it happens, then of course, after you have thermal dissipation, and this is where our nanoparticle hit. Okay, so what happened if we have light emission, then it means that we can also study the plasmon that we excite through light excitation, so light detection. So let's see how EELS and CR are connected and what kind of property are we probing when we are looking at the cathodoluminescence signal coming from an excitation of a nanoparticle with an electron beam. But okay, yes. So you remember this beautiful formula that we saw before? You can interrupt me if you have questions, of course. And so the question is, okay, if I try to do the same thing for cathodoluminescence, what is the probability of detecting light when I'm exciting with an electron, depending on the position and the frequency? So this is the formula that you can come up with. And this is those formulas true for the quasi-static state. So for a plasmon between 1 and 100 nanometer, let's say, and a nanoparticle from 1 to 100 nanometer. And you can already see the difference. So first, here we have the imaginary part that we discussed before, and this time it's the module. So it's the same mode susceptibility, but here we are looking at the imaginary part, which is why we are looking at optical extension. While here we are looking at the module of the model of the susceptibility. And therefore, this is why we are only looking at radiative and coupling to the far field of your mode. What's also interesting is that you have here a term that depends on the dipolar moment, which means that the only thing that radiates is dipolar mode. Okay, so there is a lot of modes that are not emitting light. So if you're looking at EELS, you will have what they call dark mode that are not going to be visible in cathodoluminescence. And that's really important to keep in mind. So if, for example, you compare using the same microscope, the same triangle here, so that's work from Arthur Luskin and Mathieu Kossiak, where basically they were able to measure at the same time on the same nanoparticle the cathodoluminescence, so the light emitted, and the EELS for every position. And that's just a curve of the energy depending on the position. Sorry, a map of the energy depending on the position. You can see that for EELS, we see basically two different energy. We see one at the tip like this, or around maybe, yeah, something like 2 eV, and another one here in the middle, which is basically the second mode, that is more in the green, right? Around, yeah, 2.9 eV, something like this. But if you look at CL, you only see the first one. The second one is basically not emitting. It's not visible on the spectrum, because the second one is not a dipolar mode, and therefore it doesn't radiate, and you cannot see it in cathodoluminescence. So with this, we talk about the dipolar mode of the nanotriangle, and I have a question for you, I think. Yes, oh, sorry. I'm going a little fast. You have a nanoparticle. We talked about the emission and the scattering, but actually what you saw is that what I'm looking at is the coupling to the far field of a plasmon mode, which means that in a way, this is the same photon coming in and coming out. And therefore, we cannot really talk about emission. And the only thing that we will have if we look at a nanoparticle is actually scattering. The way I'm doing the difference between scattering and emission, of course, that can be debatable, is that in a way, the scattering is just the same photon going in and out, so same property. And the other one is when you have a change and you're basically inside your nanoparticle, you're creating a photon. So basically, it means that the light going out actually is the same kind of property that the light coming in. Okay, so if we do cathodoluminescence, you can actually map this plasmonic structure, and you can do it because you're looking at the light coming from the sample. You don't necessarily need your electron going through, which means that you can actually do it in a scanning electron microscope or in a transmission electron microscope. And if you do it in a scanning electron microscope, that has quite a nice, interesting. So what's quite interesting is that first, you can do much more bulkier structure. You don't need to be at your very small particle like triangle, for example, which is maybe a third or half of the paper on the plasmonic in EELS. You have a much bigger mirror because you have so much space, which means that you're quite efficient to collect the light, which for plasmon is quite important, right? Because of course, you have your electron exciting your plasmon, but after we saw that there were so many ways to have decoherence. And therefore, only a small part of those plasmon that are excited by your nanoparticle are going to create light. So you have a very weak signal. So being able to collect as much photon as you want is actually quite interesting. Of course, if you're inside an SEM, your spatial resolution is going to be above 10 nanometers, so that could be a problem. And because you don't have access to EELS, then you're, of course, limited to your radiative mode. If you do it in an STM, then you can have EELS and CL at the same time, which is always nice. You have a much better spatial resolution. And you have, but you have a light collection that is drastically reduced. And you have to be thin sample, so you're quite limited in what kind of nanoparticle you can actually look at. And I think, yeah, that's what I thought. I have a question for you. I just show you a lot of map of a nanotriangle, but the question is, why do I have a dipolar mode for a triangle that has 3 hotspots instead of 2? You should be able to start answering. It's working. Yeah. Is it working? Yeah. Okay. Okay. So most of the people answer first mode equal dipolar. Well, actually, the right answer was there is more than one dipolar mode that you see here, but you're not able to distinguish them if you use EELS. So how can you do it? Well, you can actually do it quite easily, in a way, using cathodoluminescence. There is something I didn't mention in this formula, something that was a little under the carpet, is this integral that you see here over something called omega d, which is actually the different angle of your parabolic mirror. But if you're actually able to resolve the different angle, you're actually able to resolve in momentum. And if you also resolved in polarization, then you have angle and polarized resolution, which means that you're able to distinguish the different mode. And if you now relook at your triangle and you look at your light, so you basically filter in polarization, in angle, and of course in frequency, what you can see is that you have one dipolar mode, which is between here, and another one between here and here, which is something that, of course, you cannot see when you just look at your non-resolved triangle. So that's a nice thing to do. And I think one of the things that I like about catoluminescence is that you have your light, and after you can do anything that you want with your light that is so difficult to do with your electron beam. You can filter polarization, you can filter in angle quite easily. So that's much easier to do. You can do it outside of vacuum, do a lot of things outside of vacuum that you have to do in vacuum if you do it with EELS, which is basically like trying to resolve momentum in EELS. Of course, that's possible, as you could see with the talk of Jordan, but it's of course much more difficult. And you can also try to resolve polarization by shaping your electron beam before interacting with your sample to be able to select a specific momentum, a specific polarization, more specific polarization of your plasmon. That's also possible, but that's much more difficult than just putting a polarizer on your light collected by your, from your parabolic mirror. Of course, if you do this with EELS, you also have access to some information that are not inside the light cone that, of course, you cannot resolve with catoluminescence. Both are complementary. I'm not saying otherwise. Okay, so that was actually the first part of my talk, which was how we can look at plasmonic with electrons. As I said before, we have actually emission from a nanoparticle that is what we will call scattering, that basically keep the property of your plasmon mode that you excite with your electron beam. And you can look at the absorption, looking at your EELS spectrum also. If you do cathodoluminescence, then of course you're not going to be able to resolve this kind of dark mode that you can see in EELS that are present in your absorption spectrum. Okay, we talked about nanoparticle and metallic nanoparticle. We can now try to see what we can do with semiconductor. Is there any question before I'm starting? Yeah. I can repeat the question.
Mentioned that the plasmon decay in energy, so they decay. There is a damping of the plasmons, and I saw somewhere that it could be due to the scattering inside the metal. So that means that the width of the resonance line that you observe by EELS or by catoluminescence is directly a measure of the transport properties of your material?
Absolutely. So the width of your plasmon in EELS is going to be completely connected with your damping. So you basically can go back to the lifetime of your plasmon by measuring the width of your EELS spectrum, in your EELS spectrum.
But that's assuming that the damping of the plasmon is dictated by the resistivity of the material. But there are other channels of dissipation, I guess, no? Or not?
That's a good question. I'm maybe not the best person to answer. I would say that it's the same than if you look at luminescence in semiconductor. The way is that they're all going to participate. You're going to look at the width of the damping that actually take into account all those different mechanisms, and not only the scattering.
So that the width.
The width is, I think,
not directly related to the.
I think it's directly the decoherence. Yeah.
Thank you.
No more questions.
Okay, so you're going to completely another field in a way, which is semiconductor. If you look at material science, let's say it's a little two fields that for now are not talking too much to each other. And so I have no idea if the audience is more about metallic nanoparticle or semiconductor. So I'm going to be as basic with semiconductors as I am with metallic nanoparticle. And we are going to define a semiconductor just by the distance between his valence band and his conduction band with what we call the energy gap, right? And inside your valence and between your valence and your conduction band, you can have trap that is basically, for example, defect of your material, another atom, or a vacancy. And you can define different way of looking or exciting this region of your semiconductor, right? You can have an electron coming from your valence band up to your conduction band, and that's usually what we call an electron hole pair. You can have what we call an exciton, which is just an electron hole pair that is bound with each other. Or you can have an electron in a trap state and a hole inside the valence state, or the opposite if the trap is close to the valence band. Okay, so how can you look at all of this using electrons? Well, if we send an electron into a semiconductor, usually that's what happens, especially if you have a thick sample, a low energy electron, maybe 30 keV, you're going to create a lot of different interaction. And if you look in detail, actually in 80% of the case, what you're going to create is a bulk plasmon that's going to lose its coherence, creating a very high energy electron hole pair, way above the band gap of the material. And then from this really high energy, it's going to lose energy through non-radiative process with phonons up till the moment where it reaches the band gap. And here you can see that you have your electron at the band gap, your hole at the valence band. There is this huge channel between them, so there is no connection between the property of your bulk plasmon and your electron hole pair. There is a full channel of decoherence here. But those electron hole pair here now can recombine emitting light or phonons, which means that the light that you're going to come from here, that's what we call bulk excitation in cathodoluminescence. Then in this case here, it's completely connected to the optical property of your material. It has nothing to do with your electron. And that's super nice because it means that we can have the resolution of our electron beam, but looking at the optical property of your semiconductor, and especially, for example, measuring the band gap. But we have to keep in mind that this is incoherent excitation, which is really different to all the talk that we hear today and even from the first part of this talk. This is what happened in almost, more than 80% of the cases, and what most of the light coming from the semiconductor when you excite with an electron is coming from. However, as we saw before, your electron can also couple directly, for example, to the exciton of your material. So just sending exact number of energy to upgrade an electron to the band gap and basically creating an exciton state. And in this case, what you will see in your energy loss is exactly the energy of the electron minus the exciton. So that's now something that people can do, especially in 2D material, because you need something thin, because you're looking at electron energy loss spectroscopy, and as Jordan said, especially in HBN. But what you're going to be able to do is basically look at the excitons, depending of, for example, of the thickness here. For now, I'm going to talk mostly of bulk excitation, and we will come back to this. Yeah, sorry.
How do you know that you are giving exactly that energy and is not in this decay process?
Because if it was, well, because you're looking at your electron after. So if it had created a bulk plasmon, it will have an energy of maybe 20 or 30 EV, loss an energy of 20 or 30 EV. It will not have lost an energy of just 2 EV, which is the exciton. So if you see a peak like an electron just losing 2 EV, you know that it directly interacts with an exciton. Is it clear or?
Yeah, it's okay. So the way, so yeah. So in radiation chemistry, usually you populate the higher excited state first, and this goes down to the ground states.
That's happened in most of the cases, but you still have those things that can happen, but usually it's so small that you cannot really see it. And since we have monochromator, that people are really starting to see basically exciton, because usually it's a much lower energy. But I mean, usually what people are looking at is this kind of excitation. And you can actually see the difference. And here it's the beginning of the bulk plasmon, and you see that it's like crazy compared to those really, really small things here.
You're exciting a plasmon, and then the same electron beam is picking up the signal from this.
Yes, true. But in this case, if you look at your EELS spectrum, you will see only excitation of a bulk plasmon. But you will see excitation from the exciton if you look at the optical property. So basically, well, it's just to sell cathodoluminescence. No, I'm kidding. But basically, the idea is that whatever is the excitation, bulk plasmon or excitation directly by an exciton, what you will see if you look at cathodoluminescence is the emission from the band gap. Okay? I will talk a little more tomorrow how we could maybe start to distinguish between the two. But for now, let's say it's the same thing. Okay? Either we have a direct excitation, which is a very, very small percent of the excitation. If you look at the light coming out for the exciton, you have a very small part that is coming from a direct excitation, but it's really, really small. And most of it is going to come from this incoherent excitation where you excite a bulk plasmon, and it's basically decay to the band gap. Okay. Okay, so I will start with another question, which is, in which field do you think that cathodoluminescence is actually the most used? Oh, sorry. Yeah, I'm still a boomer. Yeah, you can go. Okay. I didn't hear. Sorry. Okay. And whoa, this is really split. But actually, the answer is geology. There was the answer on the slide. Come on. So there was like a split between lead technology and geology, and we will go back to this. It's starting to grow and grow and grow since more than 10 years now, but geology is still the winner. And the reason why is actually that if we go back to our valence and conduction band, and as I said, you have all those different defects, and in rocks, it's a mess. So in rock, you have a lot of different composition, you have a lot of defects, it's a mess. Like everywhere you look, it's a mess, but it's only atomic defect, right? So how do you make sure that you actually detect them? How do you know if you have one or everything? Well, if you just send an electron on your rock, then you will be able to probe all of those different things, because you will have some different energy level for your vacancy, your rare earths, your doping and everything. Which means that for rock, for example, then you will have different peaks that are associated with those different defects. And you can, in one row, look at all of this just by taking a spectrum at all the different positions. So that's why cathodoluminescence was so used in geology, and for a very long time, that was basically the only field where it was really used for different reasons. First, that if you look at the scale here, you can see how much they really don't care about spatial resolution. So in this case, they are not using electron because of the spatial resolution. They are just using them because it can excite all of this. So it's going literally with what Jordan was saying before. So they basically really didn't need a really good microscope. They were doing this in an SEM. Because it's so thick, it's actually super, super bright. So it's the same. You don't really need a high collection efficiency, all of those things. You really don't care. So they were the only one using it. That's why usually when you're saying to people that you're doing cathodoluminescence, they say, oh, these old techniques are just for geology. But of course, it changed. But it's still interesting to actually look at this and look at the scale here and to think about exactly what is the spatial resolution when you're talking about cathodoluminescence. Because this actually is something that we have to think about. Because as we saw before, if you have your bulk material, yes? You have a question about geology? I'm not sure I can answer. Huh?
Not about geology. The contrast of the previous image. So you see here facets, no? Or what?
You have a question about geology. You're really going to ask me a question about geology.
It's twinning. Okay. So this is flat, completely flat.
Yeah, it's flat. Yeah.
So
You can see
somehow-
the secondary image here.
Somebody polished the rock. No?
Yeah, I can imagine.
Okay.
I have no idea.
And the different contrast.
It's just beautiful. Why are you?
No,
I'm
it's
kidding.
nice.
Go on.
And the contrast you see in the upper image.
This is intensity. So that's cathodoluminescence. So I guess this is filter at a certain energy, and you can see that depending of the position on the rock, you have different intensity.
Okay. Because it's filtered, you see some
Yeah, so
brighter and darker.
Yeah, you're absolutely. Yeah, I should have mentioned this, even if it's for geology. This is beautiful, but it's more than this. This is just an intensity map. So it's at a specific wavelength, and you basically look at the emission depending of the position of your electron beam. Okay. And so here you can see that depending where the electron is, you actually collect less or more light. And so it seems that in this rock, which is zircons, apparently, you have different intensity depending of which phase or which part of the rock you're looking
And
at.
now you are going to explain us.
Yes, of course. I think so, hopefully. You can ask me the question at the end if you would like.
Thanks.
Okay, so let's go back to spatial resolution. Oh, but you're right. I completely forgot to explain this map. That was really bad. So you have your bulk material, you send your electron, you have your pair of interaction like this. So you're actually creating a lot of different energy. This can be quite huge depending of the thickness of your material, the energy of your electron. So already here, you lose a lot of resolution. And with this, you have to add the fact that your electron is going to create electron hole pair, and they are going to migrate. So you actually have electron hole pair diffusion. So basically, if you send your electron here, you have no idea where the light is coming from. And that's a very important part. We know where we excite, but we don't know where the light is coming from. So if you do a single spectrum, you send your electron and just send it at a single point, and you look at the light that you collected, you have no idea where it's coming from. You cannot say, oh, this is this specific position. Fortunately, we can scan. No, don't give him the mic. It's too dangerous. We can scan. So you focus your electron at a specific position, and let's say that we have a part of your material that is actually emitting light. Depending if you're far away here, you're going to have just a fraction of your carrier that are going to reach your color center or your point of emission, right? And if you put your electron just above it, then of course there is more carrier coming to this center of emission, and therefore you will have higher intensity. And so basically, and you go after, and it's the same, right? You have less emission. So if you map, you're actually able to look at a much more at a higher resolution that you will get if you have a single electron. So that's an example I really like from Louis Tizen and Mathieu Kossiak. So it's inside the TM. And what they look at is actually single defect inside diamond. So it's just a single, what we call nitrogen vacancy, right? So it's just a nitrogen that replaced a carbon and a vacancy close to it. And another defect that I have no idea what it is, but has another color on the spectrum. So if you look at the spectrum here, you have those two different specific defects here. And if now you filter the map, so you look only at the photon coming from at this specific energy, depending of the position of the electron beam. And you can see that you have a higher emission when you're on the cross here. Compare that if you're looking now at this one, then on the circle here. And so you can actually localize them with a much higher resolution than just the pair of interaction. Because if you look here, the diffusion, actually when I'm here, I'm still exciting this center here, right? So you have a huge diffusion of your light. Okay, so if you're able to map your sample, you're able to have a much higher spatial resolution than just what you can get just taking into account the electron hole pair diffusion and the pair of interaction. And what it also means and what also shows is that you're actually sensitive up to the atomic defect, which if you try in EELS to look at a single atom within a huge, like this, a huge matrix of diamond, you will never see this like single carbon. It's really, really, really difficult. And here you can very nicely see the light coming from it. Is it clear for everyone?
So why do we see such a difference in the localization of those two defects? Shouldn't the carrier dense or carrier diffusion be the same for both defects?
Yeah, that's actually a good point. My first answer would be yes, you're absolutely right. The electron hole pair diffusion should be the same. I think here it's just a question of intensity. So if you look here, the intensity is 250, right? So it's much less light. So maybe you still have carriers, but you have so little light here that basically when, yeah, you don't see it. It's 1 photon every millisecond, something like this. So the probability is too low. So maybe they're rich, but the probability is too low. Okay, so actually here I already talked about something inside a TEM, which is of course also a way of reducing or improving your spatial resolution, right? Because of course your pair of interaction here is drastic because you have a bulk material, you have a low energy electron. If you increase the energy of your electron beam and you go to thin sample, of course you're much closer to a single electron matter interaction. So let's say a single creation of single bulk plasma per electrons. But that comes with a lot of inconvenience. The first one is that you have to put a parabolic mirror within your TEM, and usually your pole piece is actually quite small. So you have a detection efficiency that also going down drastically. And we'll see that it's especially a problem if you want to do time result, for example. Okay, I discussed a lot. So single defect in nanodiamond, we also saw geology, but this of course is a strong field that is like really growing and growing even more now that we do it in TEM, which is looking at semiconductor heterostructure, where here you will have, so basically the idea is that you have different materials with just a few atomic layers. And because of this, then if you look at your conduction and valence band, you have those kind of trap here that's basically that the band gap of your material is different if you're on the aluminum nitride that is here or if you're in the gallium nitride, which means that you can basically trap your carrier within those well. And they're going to be confined in space. And because they cannot move so much, then you will have a very specific level of energy for your photon to recombine. And you have a really precise control of the emission wavelengths. That's basically the idea of LED technology, but of course it means that you're completely connected to the thickness of your gallium nitride here, the exact composition of it. And so being able to probe with your electron beam each of those different quantum well individually is actually really nice. So that's just one of the examples that you can have. I put a few here, but there is so many now, where you basically can look at the emission property of individual quantum well within here a nanowire of gallium nitride. And you can see that depending of the quantum well here, you have different photon energy. So here it's like false color coded. And you see that depending of the position of the electron beam and the quantum well that you're actually looking at, you actually have different energy. So that's actually quite nice because you're inside an electron microscope, you can actually also connect it to your structural information. Okay, I'm going to go back a little with EELS versus cathodoluminescence. With a very quick example, this paper is from Sophie Wu and Louis Tizet from Orsay. and they basically looked at the optical property of a two-dimensional material within a hexagonal boron nitride, if there was or not graphene between the hexagonal boron nitride and the 2D material. And they see some very nice difference of the exciton. So they have a monochromator, of course. You could not do those kind of study if you don't have a monochromator. And they see a shift of the exciton depending if there is the graphene layer between your boron nitride and your 2D material. Okay, so here this is for the two different positions depending if you're on the graphene or here. And I love this example because of course you need to have a monochromator, but you also need to have a really high spatial resolution, right? Because in optics you will just being able to maybe excite all of this, or they would be quite difficult to look at. But also because what you can do is actually looking at CL at the same time, and that's actually super nice, because you can see, so here this is cathodoluminescence and EELS. So EELS is the nice thing that has no noise here, and cathodoluminescence is the very messy stuff that you see overlaid. What you see is that first, if you have graphene, you have a huge emission quenching, right? Your signal is really, really low. You don't have so much of emission coming from your exciton. But when you have you don't have graphene, then that's okay. What you can also see is that you definitely have a shift between your emission and your exciton on your EELS spectrum. That's basically your Stokes shift. It's basically the difference between your absorption and your emission. And you basically can see it with doing this study comparing cathodoluminescence and EELS. That's actually quite nice. Okay, I will finish on something that maybe we don't talk enough when we're talking about cathodoluminescence, which is damage. So we all know damage in electron microscopy. As soon as you have a high energy electron, then of course you're able to move atoms, you're able to destroy your sample. The problem is that with cathodoluminescence, as we saw, we are very, very sensitive to the defect trap and everything, which means that if you move a single atom, you can completely destroy your luminescence because you will have some non-radiative channel that were not there before. And so usually if you have a sensitive material, the first thing that's going to disappear is cathodoluminescence. Usually you have people come in and say, oh, I would like to do cathodoluminescence on my perovskite, for example. And they say, no, they are super resistant under the beam and everything. We don't see anything in the HIDF image when we move. And in cathodoluminescence, I can look at them of maybe 100 milliseconds, and that's it. And it completely disappears. So here, this is typically what happens when you have some damage with your electron beam. You basically have suddenly you're basically scanning your beam, and suddenly your signal, the intensity of your signals drop rapidly. If the intensity drop rapidly from one pixel to the next, this is damage. Don't start thinking that you have a super nice spatial resolution. This is just damage. And it could be quenching if it's going back and forth like this, or it can just disappear and never appear again, okay? And there is a solution that exists, and it's actually quite nice, even if for now it's not used so much in different labs, but that's also something done from Meuret, where they start doing random scanning for cathodoluminescence. And if you do that, you avoid to have like some of the dose depending on the position of the electron beam. And therefore, you're able to remove those kind of quenching here and protect your sample. So that's the same area, but looking at random scanning and looking at a scanning beam. A nice way of also improving your cathodoluminescent signal and avoid damage is low temperature. That makes a huge difference. So I cannot do, in my lab, I cannot do like even nitrogen temperature, and they can an Orsay, and sometimes I'm really crying of how long they can look at the sample. We can, for example, perovskite, they can look for a day at nitrogen temperature in cathodoluminescence, while I have maybe 1 second. The difference is huge. It's really amazing. Okay, so I will conclude this part for cathodoluminescence. We have this time also absorption. We're also having an electron that basically can excite anything inside our semiconductor, which also means that we are going to see everything, which could be a problem if you want to look at a specific transition, that could be a problem, and we will discuss this tomorrow. That can help you to actually identify single atomic defect, but you have to keep into account that if you look at the optical property in semiconductor using an electron beam, for now you're mostly going to look at incoherent emission and not really at what's happening with your electron beam. Okay, so I can stop here or do a last part, but I think we're all tired and I can do it tomorrow.
But there's still time for questions.